4 ways to represent a function. Functions arise whenever one quantity depends on another. We usually consider functions for which the sets D and E are sets of real numbers. The set D is called the domain of the function. The number f of x is the value of f at x. The range of f is the set of all possible values of f of x as x varies throughout the domain. A symbol that represents an arbitrary number in the domain of a function f is called an independent variable. A symbol that represents a number in the range of f is called a dependent variable. It's helpful to think of a function as a machine. If x is in the domain of the function f, then when x enters the machine, it's accepted as an input and the machine produces an output f of x according to the rule of the function. Thus we can think of the domain as the set of all possible inputs and the range as the set of all possible outputs. Another way to picture a function is by an arrow diagram. Each arrow connects an element of D to an element of E. The arrow indicates that f of x is associated with x, f of a is associated with a, and so on. The most common method for visualizing a function is its graph. If f is a function with domain D, then its graph is the set of ordered pairs. Notice that these are input-output pairs. In other words, the graph of f consists of all points in the coordinate plane such that y is equal to f of x and x is in the domain of f. The graph of a function f gives us a useful picture of the behavior or life history of a function. Since the y-coordinate of any point x and y on the graph is y is equal to f of x, we can read the value of f of x from the graph as being the height of the graph above the point x. The graph of f also allows us to picture the domain of f on the x-axis and its range on the y-axis. Example 1. A. Find the values of f of 1 and f of 5. B. What are the domain and range of f? Solution. For A, we see from the graph that the point 1 and 3 lies on the graph of f, so the value of f at 1 is 3. In other words, the point on the graph that lies above x equal to 1, is 3 units above the x-axis. When x is equal to 5, the graph lies about 0.7 units below the x-axis, so we estimate that f of 5 is approximately negative 0.7. For B, we see that f of x is defined when the value of x is from 0 to 7, so the domain of f is the closed interval of 0 and 7. Notice that f takes on all values from negative 2 to 4, so the range of f is the closed interval of negative 2 and 4. Example 2. Sketch the graph and find the domain and range of each function. A. F of x is equal to 2x minus 1. B. G of x is equal to x squared. Solution. For A, the equation of the graph is y is equal to 2x minus 1, and we recognize this as being the equation of a line with slope 2 and y-intercept negative 1. Recall the slope-intercept form of the equation of a line which is y is equal to mx plus b. This enables us to sketch a portion of the graph of f. The expression 2x minus 1 is defined for all real numbers, so the domain of f is the set of all real numbers, which we denote by r. The graph shows that the range is also r. For b, since g of 2 is equal to 2 squared which is equal to 4, and g of negative 1 is equal to negative 1 squared which is equal to 1, we could plot the points 2 and 4, and negative 1 and 1, together with a few other points on the graph, and join them to produce the graph. The equation of the graph is y is equal to x squared, which represents a parabola. The domain of g is real numbers. The range of g consists of all values of g of x, that is, all numbers of the form x squared. But x squared must be greater than or equal to 0 for all numbers x and any positive number y is a square. So, the range of g is close an open interval of 0 and infinity. Example 3. If f of x is equal to 2x squared minus 5x plus 1 and h must not be equal to 0, evaluate f of a plus h minus f of a divided by h. Solution. We first evaluate f of a plus h by replacing x by a plus h in the expression for f of x. Then we substitute to the given expression and simplify. There are 4 possible ways to represent a function. First is by verbal representation or a description in words. Second is by numerical representation or a table of values. Third is by visual representation or a graph. Lastly, is by algebraic representation or an explicit formula. If a single function can be represented in all four ways, it's often useful to go from one representation to another to gain additional insight into the function. In example 2, for instance, we started with algebraic formulas and then obtained the graphs. But certain functions are described more naturally by one method than by another. In the next example we sketch the graph of a function that is defined verbally. Example 4. When you turn on a hot water faucet, the temperature T of the water depends on how long the water has been running. Draw a rough graph of T as a function of the time T that has elapsed since the faucet was turned on. Solution. The initial temperature of the running water is close to room temperature because the water has been sitting in the pipes. When the water from the hot water tank starts flowing from the faucet, T increases quickly. In the next phase, T is constant at the temperature of the heated water in the tank. When the tank is drained, T decreases to the temperature of the water supply. This enables us to make the rough sketch of T as a function of T. In the following example we start with a verbal description of a function in a physical situation and obtain an explicit algebraic formula. The ability to do this is a useful skill in solving calculus problems that ask for the maximum or minimum values of quantities. Example 5. A rectangular storage container with an open top has a volume of 10 cubic meter. The length of its base is twice its width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Express the cost of materials as a function of the width of the base. Solution. First, we draw a diagram and introduce notation by letting W and the product of 2W be the width and length of the base, respectively, and H be the height. The area of the base is, so the cost, in dollars, of the material for the base is the product of 10 and the area of the base. Two of the sides have area, and the other two have area. So the cost of the material for the sides is. The total cost is therefore. To express C as a function of W alone, we need to eliminate H, and we do so by using the fact that the volume is 10 cubic meter. Thus, which gives. Substituting this into the expression for C, we have. Therefore the equation expresses C as a function of W. Example 6. Find the domain of each function. A. F of x is equal to square root of x plus 2. B. G of x is equal to 1 divided by x squared minus x. Solution. For A. Because the square root of a negative number is not defined as a real number, the domain of f consists of all values of x such that x plus 2 must be greater than or equal to 0. This is equivalent to x must be greater than or equal to negative 2, so, the domain is the closed and open interval of negative 2 and infinity. For B. Since g of x is equal to 1 divided by x squared minus x, which is equal to 1 divided by the product of x and x minus 1, and division by 0 is not allowed, we see that g of x is not defined when x is equal to 0 or x is equal to 1. Thus the domain of G is the set of x such that x must not be equal to 0 and 1, which could also be written in interval notation as. The graph of a function is the curve in the x and y plane. But the question arises, which curves in the x and y plane are graphs of functions? This is answered by the following test. The vertical line test. The reason for the truth of the vertical line test can be seen in the following graphs. If each vertical line, x is equal to a, intersects a curve only once, at point AB, then exactly one function value is defined by f of a is equal to b. But if a line, x is equal to a, intersects the curve twice, at points AB and AC, then the curve can't represent a function because a function can't assign two different values to a. For example, the parabola x is equal to y squared minus 2 is not the graph of a function of x because, as you can see, there are vertical lines that intersect the parabola twice. The parabola, however, does contain the graphs of two functions of x. Notice that the equation, x is equal to y squared minus 2 implies y squared is equal to x plus 2, so y is equal to the positive and negative values of square root of x plus 2. Thus, the upper and lower halves of the parabola are the graphs of the functions f of x is equal to square root of x plus 2, and g of x is equal to negative square root of x plus 2. We observe that if we reverse the roles of x and y, then the equation x is equal to h of y, which is also equal to y squared minus 2. Does define x as a function of y with y as the independent variable and x as the dependent variable, and the parabola now appears as the graph of the function h. The functions in the following 4 examples are defined by different formulas in different parts of their domains. Such functions are called piecewise defined functions. Example 7. A function f is defined by: evaluate f of negative 2, f of negative 1, and f of 0, and sketch the graph. Solution. Remember that a function is a rule. For this particular function, the rule is the following. First, look at the value of the input x. If it happens that x must be less than or equal to negative 1, then the value of f of x is 1 minus x. On the other hand, if x is greater than negative 1, then the value of f of x is x squared. First, since negative 2 must be less than or equal to negative 1, we have f of negative 2 is equal to 1 minus negative 2, which is equal to 3. Second, since negative 1 must be less than or equal to negative 1, we have f of negative 1 is equal to 1 minus negative 1, which is equal to 2. Lastly, since 0 is greater than negative 1, we have f of 0 is equal to 0 squared, which is equal to 0. How do we draw the graph of f? We observe that if x is less than or equal to negative 1, then f of x is equal to 1 minus x, so the part of the graph of f that lies to the left of the vertical line x is equal to negative 1 must coincide with the line y is equal to 1 minus x, which has a slope of negative 1, and y-intercept of 1. If x is greater than 1, then f of x is equal to x squared, so the part of the graph of f that lies to the right of the line x is equal to negative 1 must coincide with the graph of y is equal to x squared, which is a parabola. This enables us to sketch the graph. The solid dot indicates that the point negative 1 and 2 is included on the graph. On the other hand, the open dot indicates that the point negative 1 and 1 is excluded from the graph. The next example of a piecewise defined function is the absolute value function. Recall that the absolute value of a number a is the distance from a to 0 on the real number line. For example, the absolute value of 3 is equal to 3. The absolute value of negative 3 is equal to 3, the absolute value of 0 is equal to 0, the absolute value of square root of 2 minus 1 is equal to square root of 2 minus 1, and the absolute value of 3 minus pi is equal to pi minus 3. Remember that if a is negative, then negative a is positive. Example 8. Sketch the graph of the absolute value function of f of x is equal to the absolute value of x. Solution. From the preceding discussion we know that, using the same method as in example 7, we see that the graph of f coincides with the line y is equal to x to the right of the y-axis and coincides with the line y is equal to negative x to the left of the y-axis. Example 9. Find the formula of the graph of function f. Solution. The line through points 0, 0 and 1, 1 has a slope of m is equal to 1, and y-intercept of b is equal to 0. So its equation is y is equal to x. Thus, for the part of the graph of f that joins 0, 0 and 1, 1, we have f of x is equal to x. The line through 1, 1 and 2, 0 has slope of m is equal to negative 1, so its point slope form is y minus 0 is equal to the product of negative 1 and x minus 2, or y is equal to 2 minus x. So we have f of x is equal to 2 minus x. We also see that the graph of f coincides with the x-axis for x is greater than 2. Putting this information together, we have the following three-piece formula for f. Example 10. The cost C of mailing an envelope depends on its weight W. Although there is no simple formula that connects W and C, the post office has a rule for determining C when W is known. This function is described in words. Let C of W be the cost of mailing a large envelope with weight W. The rule that the U.S. Postal Service used as of 2015 is as follows. The cost is 98 cents for up to 1 ounce, plus 21 cents for each additional ounce or less, up to 13 ounce. The table of values shown in the margin is the most convenient representation for this function, though it is possible to sketch a graph. In effect, this is a piecewise defined function because, from the table of values, we have. You can see in the graph why functions similar to this one are called step functions. They jump from one value to the next. Symmetry. If a function f satisfies f of negative x is equal to f of x for every number x in its domain, then f is called an even function. For instance, the function f of x is equal to x squared is even because f of negative x is equal to negative x squared, which is equal to x squared, which is the f of x. The geometric significance of an even function is that its graph is symmetric with respect to the y-axis. This means that if we have plotted the graph of f such that x must be greater than or equal to 0, we obtain the entire graph simply by reflecting this portion about the y-axis. On the other hand, if f satisfies f of negative x is equal to negative f of x, for every number x in its domain, then f is called an odd function. For example, the function f of x is equal to x to the power of 3 is odd because f of negative x is equal to negative x to the power of 3, which is equal to negative x to the power of 3, which is a negative f of x. The graph of an odd function is symmetric about the origin. If we already have the graph of f such that x must be greater than or equal to 0, we can obtain the entire graph by rotating this portion through 180 degrees about the origin. Example 11. Determine whether each of the following functions is even, odd, or neither even nor odd. A. F of x is equal to x to the power of 5 plus x. B. G of x is equal to 1 minus x to the power of 4. C. H of x is equal to 2x minus x squared. Solution. For A, f of negative x is equal to negative f of x, which is an odd function. We can also prove that this is an odd function through a graph. As you can see, the graph of the function is symmetric about the origin. For B, g of negative x is equal to g of x, which is an even function. We can also prove that this is an even function through a graph. As you can see, the graph of the function is symmetric with respect to the y-axis. For C, h of negative x is equal to negative 2x minus x squared. Since h of negative x is not equal to h of x and not equal to negative h of x, we conclude that h is neither even nor odd. We can also prove that this is neither even nor odd function through a graph. Notice that the graph of h is symmetric neither about the y-axis nor about the origin. Increasing and decreasing functions. This graph shows rises from a to b, falls from b to c, and rises again from c to d. The function f is said to be increasing on the closed interval of a and b, decreasing on b and c, and increasing again on c and d. Notice that if x sub 1 and x sub 2 are any two numbers between a and b with x sub 1 is less than x sub 2, then f of x sub 1 is less than to f of x sub 2. We use this as the defining property of an increasing function. In the definition of an increasing function, it is important to realize that the inequality f of x sub 1 is less than to f of x sub 2 must be satisfied for every pair of numbers x sub 1 and x sub 2 in an interval I with x sub 1 is less than x sub 2. You can see from the graph that the function f of x is equal to x squared is decreasing on the open and closed interval of negative infinity and 0, and increasing on the closed and open interval of 0 and positive infinity. Is it an information overload? Relax and have a cup of milk to boost your brain, and for more videos about mathematics, subscribe to EdMath channel.